So we've been focusing on the quality of immutable objects so far in this reading. What about mutable data types? Now recall our definition. Two objects are equal when they cannot be distinguished by observation. With mutable objects, there are now two ways to interpret this. Maybe what we mean by distinguished by observation is that they can't be distinguished by observation that doesn't change the state of the objects. In other words, they can't be distinguished if you only call observer, producer, and creator methods. This is often called observational equality because it's testing whether two objects look the same in the current state of the program without changing the state. A stronger way of saying it is that they can't be distinguished by any observation, even state changes. And this interpretation allows calling any methods on the two objects, including mutators. This is often called behavioral equality since it tests whether two objects will behave the same in this and all future states. Now for immutable objects, which don't have mutators, observational and behavioral equality are identical. For mutable objects, it can be very tempting to implement strict observational equality, in other words, ignoring mutators. Java actually uses observational equality for most of its mutable data types. If two distinct list objects contain the same sequence of elements, then equals reports that they are equal, even though a mutator would find that they are different. But using observational equality can lead to subtle bugs, and in fact it allows us to easily break the rep invariance of other collection data structures. Here's an example. So suppose we make a list, add an element to it, and then we put it into a set. So we have now a set of lists of strings, and we're going to add this list to that set. Now we can ask, does this set contain the list we just put into it? And yes, the answer is yes. But now suppose we mutate the list. So it used to have just A in it. We've now added goodbye to the end, so the list has A and goodbye. Now we ask, does this set contain this list? The answer is false. But it's worse than that, because when we iterate over members of the set, we still find the list in there. But contain says it's not there. So look at this. So we are iterating over the lists that are found in this set. So L is going to take on the value of each list that is found in this set. We're going to get an L out of that list, out of that set, I'm sorry. And then we're going to ask for this L that we have just found in the set. It's coming out of the iteration of the set. Does the set contain that L? The answer is no. This clearly violates what we expect contains to mean and what we expect iteration to mean. They disagree now about whether an element is in the set. The set is clearly broken. You can see this code in action if you go to the online Python tutor with that link. So what's going on? Well, list of strings is a mutable object. In the standard Java implementation of collection classes like list, mutations affect the result of equals and hash code. When the list is first put into the hash set, it's stored in the hash bucket corresponding to its hash code result at that time, which uses only the element A. When the list is subsequently mutated, so it has an A and goodbye on it, its hash code changes. But hash set doesn't know about that, doesn't realize it needs to be moved to a different bucket. So when contains goes and looks for it, it can never find it. The iterator, on the other hand, doesn't suffer from that problem. It's just going through the hash buckets one at a time and not actually trying to look anything up using its hash code. So when equals and hash code can be affected by mutation, we can break the rep invariant of a hash table that uses that object as a key. Here's a very telling quote from the specification of Java util set. Great care must be exercised if mutable objects are used as set elements. Behavior of a set is not specified if the value of an object is changed in a manner that affects equals comparisons while the object is an element in the set. The Java library is unfortunately inconsistent about the way it interprets equals for mutable classes. Collections use observational equality, but other mutable classes, like string builder, use behavioral equality. The lesson we should draw from this example is that to be safe from bugs, equals should implement behavioral equality. That means two references should be equals if and only if they are aliases for the same object. So mutable objects should just inherit equals and hash code directly from object because that's what it already implements. For clients that need a notion of observational equality, whether two objects look the same in the current state, it's better to define a completely new method that won't interfere with the way equals in hash code and hash tables behave. We might call it, for example, similar. So here's the final rule for equals in hash code for abstract data types. If you're writing an immutable data type, then your equals should compare abstract values. It's the same as saying that equals should provide behavioral equality. And hash code should map the abstract value to an integer. So immutable types must override both equals and hash code. For mutable types, equals should compare references, just like equals equals does. This is the same as saying equals should provide behavioral equality, but also referential equality. And hash code should map the reference into an integer. So mutable types should not override equals in hash code at all, should simply use the default implementations provided by object. Java doesn't follow this rule for its collections, unfortunately, which leads to the pitfalls that we saw above.